the gas laws, we'll be looking at, whoa, what happened there to my, so we're looking at gas laws, and this is section 10.3 in your book. The very first gas law that we are looking at is Boyle's law. So this is called Boyle's law. Boyle's law is a relation between the pressure and the volume of the gas. So if we look at this sample of gas, notice there are 5 samples of this gas, 5 gas molecules, which makes it a little bit easier. Now what pressure is, remember, is pressure is the collisions between the gas molecules and the sides of the container. That's what creates the pressure. So what happens in this is when we make the volume smaller, by pushing the lid down, well, we're going to have more collisions because those gas molecules have less room to move around, and so the pressure will increase. So again, pressure is the collisions with the sides of the container. If there's less room for the gas molecules to move around, there's going to be more collisions, there's going to be a higher pressure. So that gives us a relation between these values. So as the volume goes down, right, the pressure goes up. So volume goes down, we have some less room, pressure is going up, there's more collisions. So what this would be called, if one goes down and the other one goes up, and our pressure, of course, is going up. This is called an inverse relationship. So let's look at how we'd write this. We'd say that volume is inversely proportional. So this means proportional is inversely proportional. That's the 1 over P. So what that's saying is, again, as pressure goes up, volume is going to decrease. As volume goes down, pressure is going to increase. Another way we could write this is doing a little bit of algebra. If I multiplied both sides of this equation by P would cancel here, put P over here. Now we have a relation that P times V, or V times P, either way, could be equal to some constant, right? It could be equal to some constant value that isn't going to change because they're inversely related. If one goes up, the other one goes down, but they're going to go up and down at those same rates. And so they could be equal to some constant. Now we don't have that value, but what we could say is that if you have a sample of gas where the temperature doesn't change, and it's the same sample of gas. If you had, say, a sample of gas in a balloon, say 1 mole of gas, and you changed the pressure on that balloon, you could predict what the new volume would be. So P1V1, as I like to say, is equal to P2V2. So that allows us to make calculations for changes in volume or changes in pressure as long as we have a constant temperature and a constant amount of our gas. Okay, this is our first gas law, Boyle's law, volume pressure relation, inverse. Our next relation is what we call Charles' law. Charles' law. Charles, I don't know where the apostrophe goes, spoke to us about the relation between temperature and volume. This makes sense as well, is that as we add more temperature, so as this flame gets bigger, as we add more temperature, we're increasing the speed that the gas molecules are going to move. So if the pressure is constant, right, the volume will increase. Now if we kept the volume the same, if we didn't allow the volume to increase, well then the pressure would increase. But if we keep the pressure constant, if we keep a constant pressure, then the volume has to increase to maintain that constant pressure. So we know this, though. This is something you've probably seen or experienced before. Okay, so here's something we could think about. If we had a balloon, and this balloon is submerged in ice, then we take that same balloon and keep it in the same beaker, transfer it over to a hot plate, start heating it up so the water melts and then starts boiling. What we'll see is that the gas in that balloon is going to expand as well. So what we have is an increase of temperature, and as the temperature increases, the volume increases. Again, that's our Charles' law. So these things are proportional then. As volume goes up, temperature goes up. As temperature goes up, volume goes up. It's a proportional relationship. Now again, we could write an equation for that. Where some constant on one side, or again, if we put the terms on the same side, it'd be V over T equals that constant. Again, we don't know what that constant is. We just know that it is a constant. So again, just like we did with Boyle's law, we could set one of these at item 1 and temperature 1, volume 1, temperature 1, and we could say if we keep a constant pressure, if we keep constant pressure and we change the temperature, we are going to know the change in the volume because, again, they are proportional. We're a proportional relationship. One quick caveat we need to talk about before when we talk about Charles' law and temperature is that temperature is going to be on the Kelvin scale that we use. We always want to make sure we're using the Kelvin scale. What the Kelvin scale is based on is the Kelvin scale is based on the idea of absolute zero. What absolute zero is really a theoretical point. And it's been experimentally determined that if we have multiple gases and we start cooling them off, so taking them at cooling them off, what we'll see is that the pressure inside that cylinder or inside that balloon decreases. So the pressure decreases as the temperature decreases. That's a relationship that we'll see. But with any gas that we do this with, and these are just different gases, what we see is that we can only get them so cold in a laboratory setting. But if we continue those lines further down to see, they all converge at one point. And the point that they converge at is this, negative 273.15. Now, this line is in pressure right now, but it could also be in volume. Normally, when I see graphs like this, they're in relations of volume to temperature, whereas that as we decrease the temperature, it looks do they go to a point of zero volume. Well, obviously, zero volume isn't possible. It's not possible that things take up no space whatsoever. But the idea is that that is the coldest possible temperature, because at that temperature, the gas molecules are not moving. In fact, nothing is moving. There is no energy. There is no volume being occupied. So again, it's a theoretical value. That absolute zero might be a value that cannot actually be reached, kind of like the speed of light, as you can get closer and closer and closer to it, but actually reaching that value is probably nearly impossible. But our value anyway is negative 273 Celsius. Now, instead of using that Celsius scale, what we'll use is our Kelvin scale. So notice 273 Celsius is what we call 0 Kelvin, so that's the adjustment. What we do to convert our Celsius temperatures to our Kelvin temperatures is we add 273. And we do this because we cannot have negative values in proportions. There's things that just aren't going to work out correctly if we try to throw a negative value into a proportion. So we need to make sure we're always working on the Kelvin scale. Now notice our Celsius scale was just made before we knew of Kelvin, before we knew of absolute zero. But notice the degree markers are the same. If we go up 1 degree in Celsius, we go up 1 degree. Now that's different than our Fahrenheit scale. Our Fahrenheit scale is kind of goofy. So Celsius is based obviously on the freezing and the boiling of fresh water. The Fahrenheit scale, I believe, is based on like crazy weird things. It's based on, I think 100 on the Fahrenheit scale was based supposedly on like a body temperature, a warm body temperature, and 0 degrees on the Fahrenheit scale, which is down here, was based on like the freezing of salt water, which is kind of goofy because neither of those points are very reproducible. Body temperatures fluctuate, as does the freezing temperature of salt water, because it's going to depend on the concentration of the salt in the water. Regardless, we use Celsius, and when we're talking about gas laws, more often Kelvin. Obviously, this is true. Last law we want to look at is what's called Avogadro's law. And yes, it is that Avogadro. The Avogadro law. Okay. And it is that Avogadro's that gave us Avogadro's number. In this case, what he was talking about in gases is that, and he perhaps had the easiest gas law. He said the more stuff you have, if you go from 1 mole of gas to 2 moles of gas, well then the volume goes up. So the more stuff you have, the more volume it occupies, again, at a constant pressure and temperature, which is kind of a silly law. It's one we probably can figure out without Avogadro's help. But the more stuff we have, moles in this case represented by N, that's proportional to volume. So if moles go up, volume goes up, those are proportional values. Again, we could write them in relation to a constant, or, like we have here, in relation to each other, where we have N1V1 equals N2V2. So again, if we change the number of moles of a gas, we can predict what that volume will be. So you can kind of see our problem right now is we have Boyle's law, Charles' law, and we have Avogadro's law. So we have that pressure is inversely proportional to volume. we have that volume is proportional to temperature and that moles of a gas are proportional to volume. And if you're anything like me, I really would rather not memorize multiple equations and use those like P1 V1 equals P2 V2, V1 over T1 equals V1 over T2, or V2 over T2. That gets confusing. Obviously, I can't even say it. So what we do instead is we try to combine these. So these are relations we have right now: V1 times P1, V1 over T1, V1 over N1. And notice the commonality behind all of them is they're all in relation to volume. So if we wrote them all as a proportion in relation to volume, what we could do is we would have to move pressure down to the bottom over here, and we'd have to move these, temperature to the top, and moles to the top. Again, if I was going to rearrange this, and I could write this as a proportion, I could write them all together. I could substitute everything in for V1, and I don't want to write equals because it's not quite equals yet. V1 would be proportional to T1 N1 over P1. So that is a proportional symbol. So now what we have is we have volume, again, inversely proportional to pressure, which is what we're writing here, is proportional to temperature, and is proportional to moles. That's why those are on top, right? I'm just rearranging the equation to put them on top. So we have a proportionality from volume to relate to all of those. That's pretty nice. But it can get just a little bit better, because we could also put volume down on this side. And if we put volume down on that side, then what we have is T NT over P V is going to be equal to some constant. We could have a constant, it's called C for right now, so that value could be equal to a constant. So if we could figure out what C is, it would be very helpful. The other thing we could do with this, so notice this is what we just wrote. The other thing that we could do with this, so volume again, inversely proportional to pressure, proportional to moles and temperature, is we could stick these together in what we would call a combined gas law. And then we don't have to remember multiple gas laws. We could just use the combined gas law all the time. And notice what they dropped out of this one is they don't have moles. But I could put N1 here, N2 over here. Now sometimes they don't put in moles because they don't change the amount of gas. They're talking about one sample of gas. And that's how we'd use the combined gas law. So if we had a single sample of gas that didn't change the temperature, well then we can cancel that out of the equation. We can cancel the temperature out of the equation as long as it doesn't change. If it's 273 over here, Kelvin, and 273 Kelvin over here, well then there's no change, so we don't have to put it into the equation. So we can kind of use our combined gas law, and we can simplify it as needed for whatever type of equation we're doing. So that's what I would encourage you to do. We don't need to memorize Boyle's, Charles, Avogadro law separately, except for to give those open credit. We can just use the combined gas law for any types of problems that we're going to have concerning gas laws. So now what I want to do is see if I can use that combined gas law to solve some of these gas law problems. Notice if you're looking through your book also talks about Gay-Lussac's law, which I don't want to remove any credit from Gay-Lussac. He is a nice man as well, but I just tend not to need his law because I end up skipping over and going straight to our ideal gas law. And Gay-Lussac, though, if you must know, related pressure and temperature. So there's that. Anyway, let's use our combined gas law. So we said P1 V1 equals P2 V2 all over N1 T1 and N2 T2. Okay, so if I read number one, it says we have a sample of helium gas. It has a volume of 200 milliliters. So I'm going to assume those are my initial conditions. So I'm going to put this value in for V1. And it's at 0.96 atmospheres. So that is going to be my P1. Okay. It says what pressure in atmospheres, so it's asking for P2, what's my change in pressure, is needed to reduce the volume at constant temperature to 50 milliliters. So I have a new V2. So it's giving me a V1, it's giving me a V2, it's giving me a pressure one, it's asking what my pressure 2 is, and notice what it says here, at constant temperature. If the temperature doesn't change, what you can do is you can cross it off both sides. It won't affect this relation. So we can just cross it off. Notice it's saying nothing about changing the amount of gas. So if we're not adding more gas or subtracting some gas, we can also just cross off N1 and N2 as well. So essentially, we're left with Boyle's law. Now, could we have just started with Boyle's law? Absolutely, but then we would have had to memorize it separately than the combined gas law. So let me put in my numbers. Again, it's just a proportionality. So I have 0.96 atmospheres. I have 200 milliliters. And that has to equal my P2, which I'm solving for, times 500 milliliters. Of course, I'm going to want you to keep on the units, because notice what happens with the units. To solve this, I need to solve for P2. That means I'm going to divide this side by 50 milliliters. That will cancel my milliliters and my 50. Over here, if I divide by 50 milliliters, notice what happens. It cancels my milliliters, and then I divide out these numbers. I get 200 divided by 50 is 4. I have 4 times 0.96, which would be 3.84 atmospheres. So, lots of fun. Might as well do another one while we're here. Again, I'm going to start with my combined gas law for number 3. I'm not going to try to figure out which law I need. Again, we already did 2. It says a certain quantity of gas has a volume of 0.75 liters. So this is a volume, that's my V1, at 298 Kelvin. So that is a temperature they're giving me. At what temperature, in degrees Celsius, so we want a new temperature, that's where my question mark is, that's what I'm solving for, would this quantity of gas be reduced to 0.5 liters? So 0.5 liters is my second volume. So I have a V1, I have a V2, I have a T1, and I'm trying to solve for T2. So notice it says a certain quantity of gas, so we don't have more or less gas, it's the same quantity. And notice it says assuming constant pressure. So I can cross off my pressures because they're not changing. So notice I am left with Charles' law, that's what I'm using. But again, instead of remembering which law is which, I just like to use the combined gas law. So I have 0.75 liters over my initial temperature, 298 Kelvin. Again, in our calculation, it has to be in Kelvin because we're doing proportionalities. We can't have anything that could potentially go into a negative value. It would not work or make any sense. So we're solving for a T2. Well, the first thing I want to do is if I have my unknown on the bottom, I'm going to flip both sides because I want my unknown on top, preferably. So I'm going to flip both sides. I'm going to flip my equation around. So I'm going to say T2 over 0.5 liters is equal to 298 Kelvin over 0.75 liters. And again, I can do that because I flipped both sides. You can do whatever you want to equation as long as you do it the same as both sides. I'm going to multiply this side now by 0.5 to get rid of it. So I'll multiply this side by 0.5 liters. Again, that will, again, limit out my liters. I have 0.5 over 7.5 times 298. Notice what is happening is my volume is decreasing, so my temperature has to decrease. So my T2 now is about 199 degrees Kelvin. Again, if we look back at the question, though, it said what is going to be our temperature in degrees Celsius. So after we're done, then we have to change it to degrees Celsius. So again, our Kelvin temperature is Celsius plus 273. So if I'm solving for the Celsius temperature, I have to take Kelvin minus 273. So I'll have to subtract 273 from this value. If I subtract 273, my T2 is about negative 74 degrees Celsius. So pretty cool. I'm going to get pretty cold to maintain that constant pressure. Last one I want to do here with you is number 6. So it says we have a certain mass of oxygen was collected over water when potassium chlorate was decomposed in heating. Okay, so we have a mass of oxygen. Remember, oxygen is O2, by the way. The volume of the oxygen sample collected was 720 milliliters. So 720 milliliters. That's my volume. I'm going to say volume 1 at 25 degrees Celsius. So my T1 is 25 degrees Celsius. Now be careful with that. Again, degrees Celsius is not going to work. I'm going to have to put that into Kelvin. And a barometric pressure. Ooh, so notice I have all these conditions of 755 torr. Now it says, what would be the volume of the oxygen at STP? Okay, so what we need is we need to know what STP is. Well, standard temperature and pressure, if you remember from the previous podcast, is a temperature of 0 degrees Celsius and a pressure of 1 atmosphere. So we have to do couple things here. We're solving for our V2, right? So this is our P2 and our T2. So it says, well, how are these things going to change? Notice the temperature is changing, the pressure is changing. Now, how is the volume going to change? Well, the first thing I need to do is make sure everything is in the same units. So temperature, I'm going to convert into Kelvin. So 0, that one's easy. I add 273, so this would be 273 Kelvin. Over here, if I add 273, I'm going to erase that value, if you don't mind, and write in 25 plus 273 would be 298 Kelvin. Now, the last thing I have to deal with is torr and atmospheres. So I have to convert one to the other. I suppose I'll convert my torr into atmospheres. So 755 torr, because atmospheres are a more standard unit. It's 760 torr. And how do I know this? Because I looked it up. Actually, I remember it from doing too many gas law problems, but if you don't know it, you look it up. So notice there's not a big change, but it is 0.993 atmospheres. So we're not having a huge change of pressure, but a small one. We have to make that correction. So this is really our P1. So let's write out our combined gas law again as P1 V1 over N1 T1. Now it's one sample of gas, so I can cross out my N1. P2 V2 over T2. Now notice I do have, so I'm going to put in my values here for these. So my P1 and V1 were the conditions I collected the gas at right here. So 0.993 atmospheres. And times my V1 is 720 milliliters. So sometimes 720 milliliters. All over my T1, well, T1 here was 298. That was the temperature it was calculated at, room temperature approximately. That is equal to, now on the other side of the equation, I have my P2. Well, my P2, again, we want to solve for standard conditions, so that's 1 atmosphere. My V2 is what I want to solve for. And my T2, again, is standard temperature, which is 0 degrees Celsius or 273 Kelvin. So perfect. I have it all set up, ready to go. V is already on the top, which is nice. I'll just multiply both sides by 273, divide both sides by 1 atmosphere. I'll get V2 is equal to, so I have multiplied both sides by 273, divided both sides by 1 atmosphere. Atmosphere cancel, Kelvin cancels. V2 is now equal to 655 milliliters. Now notice that makes sense, because we're talking about standard pressure, so this gas was collected at room temperature and approximately standard pressure. Notice we're talking about standard conditions, so that'd be cooled down to 0 degrees Celsius, so it makes sense that if we cool it down, hold the pressure relatively constant, that the volume of that gas would also decrease. There you go. You'll notice we missed from your book, we didn't talk about Gauge Law 6th law, because I just don't have time to talk about it. It's a fun, wonderful law, but we really don't need it. And the other one, we didn't talk about Dalton's law of partial pressures. We do need that one, but this is getting a little bit winded, so we'll take a break, and we'll do that in a part 2.